Friends, today we shall be discussing again on characteristic of gradually varied flow. In the last class also we did discuss about characteristic of gradually varied flow, and today we shall again be discussing some of the characteristic of some of the profiles that we couldn't cover in the last class. Well, just to recall or recapitulate what we did in the last class, we did discuss about the characteristic of M1 profile, M2 profile and M3 profile in mild slope profile. Then in steep slope profile, we did discuss about S1 profile, S2 profile and S3 profile. So, these 6 different profiles characteristic we have discussed in the last class, and for analyzing the characteristic of these 6 profile, we did use the governing equation of gradually varied flow for a particular case, that is wide rectangular channel, and of course we did use the Chase's formula along with that for simplifying the governing equation of gradually varied flow in a simple form, where we can get dy dx in terms of normal depth yn, depth of gradually varied flow profile y, and the critical depth yc. Of course, SB was there, bed slope SB is also required or also comes in that particular expression. And so, that simple expression was used just to have simplicity in the explanation part. And of course, we must know at this stage that we can analyze the characteristic of all this profile by using other forms of gradually varied flow equation as well. I mean, it is not necessary that we should go always for the wide rectangular channel expression. We can have other form of expression also. In fact, for some of the channel, some of the channel slope, like say horizontal slope, adverse slope, it become convenient to explain it from some other direction. Well, so that we will be discussing today. And first let us take again the C1 profile, and perhaps we remember that in critical slope, over critical slope, we can have only 2 type of profile, that is C1 and C3. Well, let us draw it. Say this is critical slope. Okay. Now, if it is critical slope, then this NDL and CDL are the same line, and that is why the zone 2 is not existing here. Rather, we have zone 1 and zone 3, and any profile forming in the zone 1 we call as C1 if it is on critical slope. So, here SB is equal to SC, and of course, it is positive. Well, so this profile C1 will be a rising profile like that, because we could see that if the flow depth y is more than yn, then we always get rising profile, and suppose this is our depth y. Well, now again writing that expression, just dy dx is equal to say SB into 1 minus yn by y whole square, yn by y whole cube using Chase's equation, and then 1 minus yc by y whole cube. That expression we got the simple form of governing equation of gradually varied flow in wide rectangular channel. Well, now again from this expression, if we see, say when for C1 profile, we can have that y is, what is our relation, that y is greater than yn and yn is equal to yc. That means y is greater than both yn and yc, and yn and yc are equal. Well, if these are equal, then we have some interesting situation here, that numerator yn by y. Okay, let us first see about the rising and falling type, that yn is less than y and yc is also less than y, both are equal, and so this ratio is, these two ratio in numerator and denominator, these ratios are less than 1, and that is why 1 minus something less than 1 will be a positive term, and this is also a positive term, and that is why SB is positive, and from that we can have the dy dx is positive, and this indicate that it is a rising profile. It is a rising profile. But another point here, so far the characteristic of C1 profile is there, another important point we need to see, that is our yn and yc are equal. So, the numerator, of course, I am not talking about the SB part, but the other part in the fraction, say numerator and the denominator are equal, numerator and denominator are equal, these two parts. So, dy dx is positive, of course, and dy dx is equal to SB, because these two ratio, I mean this ratio become 1 because these two value are equal. So, dy dx is equal to SB, what it indicate, I mean what it means physically, that we need to know. That is, you can see that slope is, this slope is nothing but SB, that is the bed slope. Now, slope of this profile, which is a rising one, of course, we have got this is a rising one, and slope of this profile is equal to SB. Now, when we say slope of this profile, then because we are talking about dy dx and slope of this profile, that means rather dy dx means the change of depth with respect to x, and when we are talking about change of depth, by depth we mean it is the depth measured from bed of the channel. So, that slope is basically with respect to the channel bed, and we are getting that this is a positive slope. So, if I draw a line parallel to the channel bed, if I draw a line parallel to the channel bed, then the slope at any point indicates slope dy dx, rather dy dx at any point indicate how much slope it is making with respect to the channel bed, because depth are measured from the channel bed here, and that is why this dy dx is equal to SB means that this slope is also SB. And if it is so, then we can see that this is a horizontal line, and this bed is making a slope SB here, and parallel to the bed we are drawing another line, and the profile is making the same SB slope in the rising direction, or in the, say we can say anti-clockwise direction SB. So, that way from these two angle we can see that this line, this profile C1 will be parallel to this line, that is the, this line is nothing but the horizontal line. So, the profile C1 will be horizontal wherever we take, at any point if we take, you will find that dy dx SB indicate that C1 profile is horizontal, This is a very important aspect that we need to know. Now, there should not be confusion that sometimes people or sometimes we may have in our mind that C1 profile is horizontal means whether depth is increasing in the direction of flow or whether it is remaining constant. So, that sort of confusion should not come. The reason is that profile is horizontal, but the bed is falling, profile is horizontal. So, depth is definitely rising. Here it is this much, here it is this much, that way if we go further depth is increasing. So, depth is increasing, that is why profile we call as a rising profile. That rising term is basically coming bed, not with respect to a horizontal line. So, whenever we are saying rising profile, whether it is M1 profile, S1 profile, or say S3 profile, M3 profile, or even C1, everywhere when we are saying rising means it is with respect to the channel bed, not with respect to the horizontal line. So, when it is rising with respect to the channel bed with an angle as B, then it become horizontal, but depth is increasing. Okay. So, that is what the C1 profile, and at upstream of course, we can see that at upstream this will meet both NDL and CDL line, and that way say at upstream it will become y become equal to yn as well as yc, but that ratio is again equal. Whatever may be the situation at upstream and downstream, this ratio is equal, and that is why that we are always getting that this profile is moving horizontally, and at upstream it is meeting the NDL and CDL like that. Okay. Then similarly, we can now talk about say okay, again downstream it will be, so at upstream at upstream again we are getting the same condition as say y is equal to, or y is almost equal to yn and yc, and we are again getting the relation that dy dx is equal to of course, when y is equal to yn, that way if we see this become 1 and this ratio become 1. So, this become 0 0, it is again becoming undefined. Exactly at this point what will happen, rather when we go one more step ahead into our next class, then we will find that in this sort of situation profile is not starting exactly from NDL or CDL. There will be some other conditions here, and that is why well for this situation, that is at upstream it will not start exactly from this line, and therefore, we may say that just at this line this is undefined. At this point we can say that this is undefined, and the profile will remain horizontal up to the point, or just when it is just above the point yn and yc. Exactly at this point it become say undefined, but just above this line the profile remain horizontal. So, in general we can say that this profile C1 is horizontal throughout its length. Well, and at downstream it will be governed by the control section, depth will be governed by the control section. We can say the depth will be governed by the control section. Okay. Then let us see that what about C3 profile, and the same diagram we can draw, that this is the critical slope as b equal to SC, and this NDL and CDL are same here, NDL and CDL are same. This is both yn and yc, and the profile is forming somewhere here, and this will also be a rising profile because it is in zone 3. Well, and following the same relation, that SB again yn by y whole cube divided by 1 minus yc by y whole cube, as anywhere in this case, in case of critical slope SC is positive of course, for any of this critical condition flow we have NDL equal to CDL. That is why these two ratio, this ratio, I mean these two value will be identical, numerator and denominator. So, this value will always be equal to dy dx is equal to SP, and of course it is positive, of course it is positive. Positive means when it is less than, when y is less than yn or yc, then this ratio will be definitely greater than 1. So, 1 minus something greater than 1 will be negative, but at the same time this will also be negative, 1 minus something greater than 1, because yc is also less than yc is also greater than y. So, this ratio will also be greater than 1, and that way this will also become negative, and That way this ratio ultimately become positive as SB is also positive, and we can have the dy dx is equal to SB and it is positive. So, we can write C3 profile is rising and again as dy dx is equal to SB and horizontal So, that way here also we are getting that this profile is horizontal like this and this angle is of course equal to SB, this angle is equal to SB and we know that this angle is SB. Okay. Then again at upstream, at downstream what will happen? Okay, first let us see at downstream again this is just before touching NDL and CDL it will remain horizontal. So, the profile will at downstream profile will remain horizontal, just up to the point where y, that is the depth is almost equal to yn and yc, or we can write that when y tends to become yn and yc, and when it will become exactly equal to yn or yc, that is again become undefined and we cannot say right at this moment. And of course, for explaining that we need to know that what is there on the downstream side and what is there on the upstream side, and those flow phenomenon will actually show us that what sort of profile will be there. Well, somewhere there can be hydraulic jump, and in that case this hydraulic jump may start from this particular point itself, and then we will not go up to the NDL and CDL line. In fact, when it is below NDL and CDL, anything when it change from, that means this part of flow is supercritical because it is less than critical depth, and if it is crossing the critical depth line, then the flow becomes subcritical, and when the flow changes from supercritical to subcritical, then we get another flow phenomenon, and that is called hydraulic jump, that we will be discussing after completion of our gradually varied flow part. And when the hydraulic jump will form means that time at that and this channel reach, this portion we will not refer as gradually varied flow, or rather it is not a gradually varied flow. So, this consideration or what will happen to the gradually varied flow just at this point will not be arising there. Well, then at downstream, similarly at downstream again we see that y is approaching 0, but again the depth cannot start from a 0 depth as we know. So, physically depth will not be equal to 0, and but if it becomes 0 somehow, then it become infinity here. So, infinity by infinity is again undefined. So, dy dx equal to infinity by infinity, that is undefined again. But you must remember one point, that this is when depth is just equal to 0, but when y tends to 0 till it is not 0, when y tends to 0, then flow remain horizontal, flow profile remain horizontal, and only when we try to express mathematically, then only we are finding difficulties what will happen just at y equal to 0, but for physical consideration or from a real situation point of view, we will not be getting that sort of situation. Well, now we need to discuss. So, we have covered M1, M2, M3, S1, S2, S3 and C1 and C3 profile. Now, we need to cover two different type of profiles. There are 4 different types of profiles forming over 2 over horizontal bit and 2 over adverse slope channel. And for explaining that situation where SB, suppose for horizontal slope SB equal to 0. Now, if we go by this expression, then we can see that if we put SB equal to 0, then this part whatever value it comes, it does not matter, dy dx become always 0. But it is not the situation. So, that simplification what we have made here will not provide us a solution or an exact answer to the situation of horizontal slope, and that is why I think that here we can have a different approach for analyzing the flow profile. And that is why let us discuss this point, that is the relationship between bed slope and depth. This is of course a known fact, we all know that. In case of our computation of uniform flow also we have discussed that part, but still we can see it very clearly that suppose if I write the equation again for say wide rectangular channel, then I can write Q is equal to 1 by n, then A means by, then r to the power 2 by 3, say y to the power 2 by 3 representing r as y, and s b to the power half or s to the power half, let me as it is say if I write it y n, this is also y n, then I will have to write it s b to the power half. Okay. Bed slope we are writing for uniform flow, that is why it is bed slope. Okay. And that we can write as Q is equal to say 1 by n, then b y n to the power 5 by 3 and s b to the power half. We could have discussed that without writing the expression for wide rectangular channel. Considering a general expression also it can be stated, but here it is a little more clear. Well, now what we can see that say for a given discharge, if our discharge is given for a given discharge Q, same discharge, then for any other depth we can write 1 by n b, then we can write it as y, suppose depth is changing, not the normal depth, 5 by 3, and then if we are writing this expression not for normal depth but for any other depth of gradually varied flow, then we need to use the friction slope here, half. Now this is 2r in straight product form, that is y to the power 5 by 3 sf to the power half, both has exponent positive. So that means if Q is same, other channel characteristics are same, B is same, then if y is more, if y is more than y n, then SF must be less than SB, then only these things will be satisfied. So, when y is greater than y n, this implies that SF is less than SB, and similarly if y is less than y n, when y depth of flow is less than normal depth, then what we are getting, that SF is greater than SB, friction slope is greater than, energy gradient is greater than SB, and that physically also we can explain when our energy gradient line, that is the slope of the energy gradient line SF is equal to SB, then we are getting uniform flow. That we know that when it is uniform flow, SB and SF are equal. So, when SF equal to SB, we are getting uniform flow. Now, for the same discharge, if our energy gradient line slope increase, slope of the energy gradient line increase, that means if SF increases, SF increases means slope of the energy gradient line is increasing. Now, if that increases, then difference of energy is increasing, then the uniform flow condition, difference of energy between the upstream and the downstream, difference of energy between the upstream and the downstream is increasing as compared to the difference of energy between upstream and downstream in normal uniform flow condition. So, what will happen? Flow will be accelerated, flow will be accelerated because the energy difference is increasing. So, flow will be accelerated, it will be moving in a more faster speed, and when the same discharge is moving in a faster speed or with a more velocity, then what will happen? Then depth will be lower than the depth of uniform flow depth, because discharge is same and discharge is nothing but the area into the velocity. So, when our velocity is increasing, area will have to be reduced, and if B is remaining same, because we are talking about the same channel. So, when B is remaining same, our depth will have to come down. So, when suppose the energy gradient line slope is reduced due to some obstruction, say we are reducing the energy gradient line slope, and then in that case depth will have to increase, flow will be retarded, flow will get retarded and depth will start increasing. So, this is what one important relationship that we need to understand, and well, that means with this understanding also we can analyze the characteristic of gradually varied flow. So, we can write, suppose this expression, original expression we had dy dx is equal to SB minus SF, well, and divided by 1 minus we had the expression q square t by GA cube, q square t by GA cube, and that expression can be, well, I am writing here, we had the expression q square t by GA cube. This expression, if we recall our earlier discussion, then we can express it as Froude number square also. And also that we could see in the last class for wide rectangular channel, we could express this as yc by y whole cube for wide rectangular channel. We express it like that, and in general we can express it at Froude number square, or this expression is there. Now, suppose again if we consider this to be, we can write it as Froude number also, or we can write in this form also. Well, I am writing right at this moment yc by y whole cube. I will say that this can be expressed by FR square, and that will also give us the idea whether this part is positive or negative. Well, now if our depth of flow y, is greater than yn, and that will happen, suppose this is our say in zone 2, say in zone 2 we can say the depth of flow will be less than yn. If it is suppose mild slope, in case of mild slope, if it is mild slope, then this is yc and this is yn. Now, if something is here, suppose zone 2, then in zone 2 say depth of flow is less than yn, depth of flow is less than yn. Now, depth of flow less than yn means we are coming to this point, depth of flow less than yn means SF is greater than SB, SF is greater than SB. So, if SB is positive and SF is negative, as SF is greater than SB, SB minus SF will become negative. Well, and somehow if it is adverse slope, then SB is suppose negative, then also SB minus SF, because SF is otherwise also greater, but still SB is negative and minus some negative, that will always also become negative. And if it is horizontal, then also we have this condition that SF is greater than SB. SB may be 0 for horizontal, SB equal to 0, but SF is greater than SB if we are talking about a zone 2 where our y depth of flow is less than normal depth, and in that case even if SB equal to 0, then 0 minus SF will be negative. From that point also we can know whether it is negative or positive. So, about the numerator we can go by that understanding, and about denominator you can see that 1 minus yc by y, again here say if it is yc and y, that condition from our earlier understanding also we can find whether it is positive or negative. And then for another understanding, suppose if we do not write this expression, if we write this expression as, suppose if we try to write this expression as 1 minus FR square, say Froude number square, that if we write in this form, okay, 1 minus f r square, because this y c by y, or we can write it as f r square, q square t by g a q. Then also we can see, of course, here we need to have that understanding, when the depth of flow is greater than y c, when the depth of flow is greater than y c, then that means flow is subcritical. Then we need to recall our understanding about this subcritical flow and supercritical flow. So, when depth of flow is greater than y c, then we can say that it is subcritical flow. And then we need to again recall what was the relationship between Froude number and this flow condition, that is critical flow, subcritical flow, supercritical flow. At critical flow, Froude number is equal to 1, fine. And in subcritical flow, Froude number is less than equal to 1. And in case of supercritical flow, Froude number is greater than equal to 1. Now, when our depth of flow will be greater than y c, then it is subcritical condition, Froude number is less than equal to 1, and so Froude number square will be again less than equal to 1, and 1 minus something less than 1 will become positive. From that point also we can see, and if our depth of flow is less than y c, depth of flow is less than y c, then it is supercritical flow. And when it is supercritical flow, then Froude number will be greater than 1. And so, when Froude number is greater than 1, 1 minus something greater than 1, because if it is greater than 1, square term will be further greater. So, 1 minus something greater than 1 will become negative. So, by applying those concepts also we can analyze characteristic of gradually varied flow. And well, then for H2 profile, definitely we will have to use this sort of understanding, because this is advantageous here. Well, let us draw one horizontal bed, and in fact you may have some question that when it is horizontal slope, then how flow will be occurring, because there is no component of, because entire flow, that is open channel flow, that for the governing force, or rather we can say the driving force, is the component of gravity force acting in the direction of flow. Well, now if it is horizontal, then the gravity force is acting, or the weight component is acting vertically downward, and so there cannot be, as the channel slope is horizontal, there cannot be any component of this vertical force acting in the direction of the flow. So, if there is no driving force, how the flow is occurring? Well, definitely when the flow is coming from one direction, there will be some inertia in it, and this sort of horizontal channel we get in a very small portion. And of course, we are talking about always in terms of total energy at upstream and downstream, and that is why we are talking about energy slope. So, even if it is a horizontal channel, or rather you forget about horizontal, even if it is an adverse channel, then also basically the surface of the flow will not be adverse, rather it will be always in the sloping downward direction, or SF will always have to be positive for the flow to occur. So, that sort of understanding will be necessary. And now say when we are talking about horizontal slope or horizontal bed, means SB equal to 0, and in horizontal, over horizontal bed we are getting critical depth line here, that is this depth is YC, and we know that on horizontal slope YN is at infinity. So, we do not know where our normal depth line will be, or rather we know that it is at an infinite distance. So, zone 1, that is not existing here. We cannot have anything beyond infinity, which should have been zone 1 beyond normal depth. So, that we cannot have here. So, the portion which is just lying above critical depth, and of course, this portion is above critical depth and it is below normal depth, because normal depth is at infinity. So, this is zone 2, this is zone 2. Well, and if we get a profile here, this will be a drawdown profile, as we know from our earlier understanding, but still we need to explain it. And this will be a profile of that kind, and if we say that this is the depth y, this depth y, here we can say that yn is greater than y and y is greater than yc. Okay. Now, with this condition, if we write the expression, that is dy dx is equal to, say, SB minus SF divided by 1 minus, well, let me write the expression YC by Y, because you are already becoming familiar with this particular expression. So, this is the relation. Now, for H2 profile, we know that Y is less than equal to Yn, and so we are writing Y is less than equal to Yn. This implies that SF is greater than, Y is less than Yn, rather not equal to, Y is less than Yn. So, SF is greater than SB. Well, now from this point, that is, in case of horizontal flow, horizontal bed, in this case again we have SB equal to 0. So, in the expression dy dx, SB is 0 minus SF. So, SF is greater than SB means it has to be positive, SF will have to be positive, because SB is equal to 0, it is greater than SF, it is positive. So, minus some of the positive terms means these terms will become negative. So, this is negative. And so, for y depth in this part is concerned, this is greater than yc, y is greater than yc. So, this ratio will be less than 1, and 1 minus something less than 1, that is positive. So, ultimately the expression dy dx, what we are getting is dy dx is negative. So, a falling profile. Okay. So, our H2 profile is a falling profile, and then at downstream what will happen? At downstream, y is approaching the critical depth. So, it is just like our discussion that we carried out earlier, y is equal to, say, yc, approximately equal to yc. Now, if y become equal to yc, then we are having this denominator, that is yc by y is becoming 1, and if this yc by y is becoming 1, this term becomes 0. So, dy dx become infinity. That we did discuss in our last class several times, that dy dx is equal to infinity. So, what we can conclude from this, the profile meet the CDL normally. Profile meet the CDL normally. So, this way the profile will be coming and it is meeting the CDL normally. Of course, for practical purpose we may not find exactly that it is meeting normally, and but we can have that it is like that, it is meeting normally, in theoretically you can say, and then it is expanding like this. And at upstream side, if we keep on going, then if we just consider that of course, in real situation, as we said, that this will be a small portion, this horizontal portion will be a small portion. There may be a situation that a mild slope is coming like this, then some portion is horizontal, then again the channel is going. In nature also we can have this sort of situation. Now, if it is like that, then at that point what is happening, this will actually indicate what will happen at the upstream end. And without considering that, just mathematically if we think that we have horizontal portion very long, then it is increasing, then at upstream we can say that y may become very large, and then difference between the yn and y, that may reduce, and we can have some analysis on that part. But for practical purpose, we can see that always at upstream, better we can write at upstream depth will be governed by the upstream condition, depth will be governed by the upstream condition. And now here we are yet to discuss another point that we will be discussing just after completion of this part, that is this flow H2 profile is, as it is greater than critical depth, it is subcritical flow. So, for subcritical flow we should start computing the flow, or we can have our control section at this point, that is this depth is fixed, and what will happen at the upstream point, that we need to compute from this side, we should calculate from this side, and then only we will be getting what will be depth here up to this point. Well, that will be coming in a more detailed way. Now, having this characteristic of H3 profile, we can now go to the characteristic of H3 profile. H2 we have discussed, and in horizontal slope again, say this is CDL, and this profile will be again a rising one, and the following the same combination or same equation, or the condition is same, yn which is at infinity, yn is at infinity, and then we have yn is greater than y, rather we can write now say yc, because yc is here, and y is at this point. So, yn is greater than yc, n is greater than y. This is the condition for this H3 profile. And now we can have the dy dx is equal to SB minus SF divided by 1 minus YC by Y whole cube. For again we are writing this for wide rectangular channel. Now we can see that for this case, that is for H3 profile, we have y less than equal to yn, just like H2 profile, this condition is also valid here. Y is less than equal to yn, y is less than equal to yn. Now, when y is less than equal to yn, we have SF is greater than equal to SB, and we have SB equal to 0. So, SB minus SF, this become negative, Well, when we are saying that SF is greater than equal to SB, it will have positive value, and minus of that any positive value, then this will become negative, and SB is 0. So, this is negative. And so, for this term is concerned, denominator, you can see that is y is less than YC. So, when y is less than YC, this ratio is, the YC by Y ratio is greater than equal to 1, and that cube is also greater than equal to 1. So, 1 minus something greater than equal to 1, that will also become negative, and as such this negative by negative, ultimately what we are getting, that dy dx, well, let me write here YC by Y, YC by Y is greater than equal to 1, and this lead to this term negative, and so dy dx is positive. So, the profile is a rising profile that we are getting, the profile is a rising profile. Now, once we get the profile to be a rising profile, then at downstream y is equal to yc. So, this will indicate again dy dx is equal to infinity. So, the profile meet normally, the CDL normally. Okay, so we can draw the profile like this. Well, then at upstream y approximately equal to 0 means y, we again this will become undefined. So, this become infinity. So, that way this become undefined. So, we should not go to that point, and for practical purpose profile is undefined, but this undefined means it is not y is approximately equal to, rather we can write when y equal to 0, then the profile is undefined, but before that you will follow the same condition what we are having. So, that part we can always put some dot here, that is this below, and when it is exactly equal to 0 it is undefined, and as I am repeating several times, again I can say that for practical purpose a profile cannot start from 0 depth. So, that condition will not arise at all in our practical analysis. Well, then let us see what will happen to the A3 profile or A2 profile. Here also we will be following the same understanding. The adverse slope means slope is like that, and critical depth, so SB is negative, SB is negative, and the profile, okay, the CDL line always we draw like that, it is parallel to the bed, we are drawing critical depth line YC, and the YN here is imaginary. So, YN is imaginary, and it will be again at horizontal slope itself it is going to infinite extent. So, it will be beyond that, and it is an imaginary one. So, it is like that. So, this zone we are referring as zone 2, and in zone 2 the profile is falling like this, falling like this. Now, that we know that in zone 2 it will be falling from this fact that dy dx is equal to SB minus SF divided by 1 minus YC by Y whole cube. Well, now again for this part, that is y is less than equal to yn again, and when y is less than equal to yn, we know that SF is greater than equal to SB, SF is greater than equal to SB, and here SB itself is negative. So, dy dx, we can say that dy dx is equal to, I mean, so far sign of dy dx is concerned, let us go to that. SB is negative and minus SF, SF is definitely greater than SB, and of course, as we know that flow to occur means SB is, SF is positive in this direction if flow is occurring. So, but this is a negative one minus, then minus some of the positive value means it will be further negative. So, this become negative, and then YC by Y, if we see that this Y depth at any point Y is greater than YC. So, Y being greater than YC, this part, this ratio will become less than 1. So, 1 minus something less than 1, cube is obviously less again. So, 1 minus something less than 1, that become positive. So, dy dx is actually, we can write that this is negative sign wise, and that means it is a falling profile, it is a falling profile. Okay. And that this denominator part is also negative, that we could see from Froude number point of view also, 1 minus say Froude number square, and Froude number because it is in subcritical portion, so it is less than 1. So, less than 1 square, then it will become again less than 1, 1 minus Froude number square will become positive. So, that way also you could have write this as a positive part. Well, so any of this form we can use. Now, so dy dx is negative, it is a falling profile. Then at downstream what is happening, that if we see again y is equal to yc. At y equal to yc, we can say that dy dx is equal to infinity, and thus the profile meet CDL normally, profile meet CDL line normally. So, it will be meeting like this. Well, and again here also the upstream flow condition will be known from the condition what is happening at upstream, because adverse slope profile cannot extend to infinite extent. It will be a smaller portion in the entire channel reach, because say otherwise when you allow the gravity flow to occur in a slope having adverse slope, flow cannot move. But in natural condition it may happen sometimes that the flow is coming like this, and say there is some rising in this part and then it is moving like that. In that case, say this part may have some adverse slope in this portion, and then flow will be actually coming like this, and this part of flow may be say A2 profile like that. And so what will be the depth at upstream? That will be governed by the flow depth here. And of course we can keep on computing from this side. We can start computing and we can come up to the end of the adverse slope point, and then beyond this, when it is coming, if it is mild slope, then we will have to compute this profile from on the mild slope bed, considering this as the known depth from the computation of A2 profile here, and then we start computing this part. So that way we are computing from this side, and this flow, if it is remains subcritical, then for all these things the upstream depth will depend on extent of the length of the adverse slope section. Similarly, in horizontal slope also, when we were discussing that part, what will be the upstream depth? That will depend on the length of this horizontal portion, because we are computing from this side, and this way we will be arriving at a point. And then at upstream what will happen? That will be decided from this particular depth. We will go like that. And of course, some other combination may be there if this slope is steep slope. Suppose supercritical flow is coming in this part. Well, that part we will be discussing later. Then let us see what will happen in case of A3 profile. The combination will be almost same. In A3 profile, this is A3, you can write that SB is negative, SB is negative, this is our CDL line, and then A3 profile will be a rising profile like this, because this is YC and the combination we have is YN is greater than YC and YC is greater than Y, and from this relation dy dx is equal to SB minus SF divided by 1 minus YC by Y whole cube. This is again from wide rectangular channel. Then we are getting that as Y is less than equal to YN, SF is greater than equal to SB, as such what we are getting that dy dx, sine of dy dx we can have, this is equal to, this part is negative, numerator part is negative, and a denominator as Y is as Y is less than equal to YC, here Y is less than equal to YC, Y is less than equal to YC. So that indicate that this ratio is greater than equal to 1, and that's why 1 minus something greater than equal to 1 become again negative. So ultimately dy dx become positive, and this indicate this is a rising profile, this is a rising profile. Okay. Well, so this profile will be rising, from that it is clear, and then at downstream point y is equal to yc. So this indicate dy dx is equal to infinity, and that indicate the profile meets the CDL normally. Okay. So I can draw the line in this way, I can draw the line in this way, and at upstream again, that at y equal to 0, this is undefined, this is undefined, but of course we can put some dot here and we can draw it like this, and again just like the earlier cases, for practical situation just y equal to 0 point will not be there. Well, now with this understanding of characteristic of gradually varied flow profile, let us discuss another topic, or which is very much related to the computation of gradually varied flow profile, that is called control section. Well, now control section in general also important for some other work related to hydraulic engineering. So, what we mean by control section? Well, it can be defined as, say, you can concentrate into the slide, we can write like this, that a control section can be defined as any artificial or natural section, that provides an unique depth discharge relationship. I should put a hyphen here, depth discharge relationship. So, in nature or sometimes artificially we make some sluice gate, we construct some weir, and we construct some spillway in dam. So, those structures are of the type that at those points we get some unique relationship between depth and discharge. That is, if we know the depth, just knowing the depth without measuring the other things, of course, because the channel section is fixed at that point, bed width, channel shape, whether it is trapezoidal, rectangular, or some special shape sometimes can be, and then knowing all those things, we know that at that point we have a depth discharge relationship. That is, for a particular depth we will be getting a particular discharge, the unique relationship, depth discharge. So, those sections which provide that sort of relationship, we call those as a control section. Now, why we are discussing about this control section in gradually varied flow analysis? Of course, in general, say a channel portion where say roughness is known, shape is known, there also we know that when in case of uniform flow we are getting a depth discharge relationship, that is also one situation. But here at a particular section we are getting a depth discharge relationship, and that relationship is very, very important for gradually varied flow computation. Otherwise also it is important because, say, for discharge measurement in a channel, many a time we are interested to know how much is the discharge flowing through the channel, and if we try to measure it directly, then we need to measure the velocity of flow at each and every section, and then at that section we need to measure velocity of flow, and as we know that velocity may vary within the section itself, across the section. So, we may have to measure the velocity at different point, then we need to measure the cross section area, and then we need to multiply this velocity by the cross sectional area, respective cross sectional area, and then we are getting the total discharge. But that exercise is very time consuming and it may not be possible for us to do it every time, and that is why when we have a section of this kind where we know the discharge depth relationship, just we will be measuring the depth and we will be getting the discharge. And this sort of things may happen when we have a weir, gate, then rock outcrop in a stream. In a stream, sometimes we have, say, narrowed down portion, rock is coming from both sides, and that way rock outcrops are coming, and at that point we can measure, or say from the bottom side, this sort of V-shaped rocks opening is there somewhere in a hilly stream, particularly we can have that sort of things. In fact, in one of my practical work, I had to measure the stream flow quantity to know that whether it is feasible for a say hydropower project, a micro hydel project. Then on the hilltop I did not have any other devices, then I could find a rock outcrop, and by measuring the depth of flow at that point, I could just calculate how much can be the discharge approximately. Well, so that sort of situations are there. Then sometimes there can be free overfall, and all those points we use sometimes as a control section. And in case of gradually varied flow, its importance is that when we have gradually varied flow, then for computing, that is for calculating the gradually varied flow value at different point, what we can have, that we need to start our computation from a known point, at least at some known point. Okay, if the profile is starting from normal depth, that is of course a known point. If the profile is starting from critical depth, that is also a known point. But if it is not starting from critical depth or normal depth, because the profile may not extend for its full length. Suppose when we are talking about M2 profile or S2 profile, well, M2 profile is starting from say normal depth to critical depth. But in nature, it is not that always we will be getting complete length of a M2 profile, it may not be. Similarly, in M1 profile also it can happen, for any profile it can happen. And if we have a control section, whatever may be the type of control section, if we have a control section, we know that at that point this will be the depth. And then we can start computing from that particular point for knowing the other value of gradually varied flow profile. Well, and then another important aspect is the subcritical flow and supercritical flow. Then in subcritical flow, I just tried to explain beforehand also that in case of subcritical flow, the control section is at downstream. That is, for computing purpose, if we get a control section at downstream, then we will be knowing that that point is fixed and depth at that point is known, and the subcritical flow occurring on upstream of that control section will be governed, depth of gradually varied flow of the subcritical flow, subcritical gradually varied flow will be governed by the depth of the control section at downstream. So, just at this point we can have that subcritical flow gets affected by any disturbance at the downstream point, that is what we can say. So, control section is fixing that things, and this will influence the flow at upstream. And in supercritical flow, if we make any disturbance or if we fix that this is the depth at upstream point, then this will influence the profile in the downstream. In supercritical flow, if we fix something at downstream, that will not influence the supercritical flow upstream. So, in supercritical flow, control is always at the upstream. So, we can summarize it like that: in supercritical flow, control is at upstream. If anything we do in the downstream, that will not influence the supercritical flow. Of course, indirectly it can influence. Suppose something we are doing at the downstream point, and that has made the profile to become subcritical at downstream point, then that subcritical flow will be affected by the measures or by the disturbance that we are making at downstream, and this may indirectly reduce the portion of the supercritical flow and hydraulic jump sort of things we can get. That we will be discussing of course later, but we can just at this point know that control is at upstream for supercritical flow, and in subcritical flow control is at downstream. Just at this moment we are giving this as a statement, and to have it in a more clear form, we need to know what is the relationship between the flow velocity, that is the velocity of the media flow velocity, and the velocity of the disturbance. If we create a disturbance, say some wave is forming, how the speed of the wave is and how this wave is moving, that we need to know, and why this disturbance is not. Suppose in supercritical flow, if we are doing something at downstream, why it is not influencing the upstream part. In subcritical flow, if we are doing something at upstream, why it is not influencing the downstream part, that we need to discuss. Well, we shall try to discuss that briefly in the next class, and then we will move on to the computation of gradually varied flow. Thank you very much.